So good morning and welcome to this final talk in our webinar series. So our final speaker in the webinar series today is Adelina. And Adelina, she is a professor at the Department of Biochemistry and Molecular Biology at the University of Southern Denmark. She also got her PhD at the University of Southern Denmark. Adelina's research work focuses on molecular aging by studying how biological molecules like proteins, lipids, and other metabolites change inside our cells with time and how that affect our ability to recover and renew our tissue to stay healthy. For that, she's using various biomolecular tools like mass spectrometry and also 3D cell structures, 3D cell culturing. So I have had the pleasure of listening to Adelina a couple of times before, and I have always enjoyed it very much. And I'm really looking forward to hearing her talk today. So without any further ado, Adelina, please enlighten us.
Thank you, Thorsten, for the very nice introduction. I will now share my screen with you, hopefully. Yes. All right. So thank you for inviting me to this webinar and giving a nice introduction, Thorsten. So as it was said, I'm working at the Department of Biochemistry and Molecular Biology of University of Southern Denmark. And my group is called Protein Oxidation and Aging Group. So so today you will actually hear a little bit more about what protein oxidations are and why I am so interested in them. And when I look back, why I got interested in protein oxidation, I have to go back to my very early childhood when I actually spent a lot of time with my grandparents. And I remember I was very sad seeing them getting old and fragile. And I asked them, why is this happening? Why can't you run with me and play with me in the garden? And I remember only one thing, that my grandfather compared himself to an old car. And I'm not sure actually if he already at that time knew what I know today, but he was not very far from the truth. So when a car rusts, the oxygen molecules from the atmosphere, they will attack the material, and they will attack the iron and change this material into much weaker, dustier and flakier and more fragile than it was when the vehicle, when the machine was new. And this is more or less the same that is happening to human bodies over time. And today, a large body of scientific research shows that these long-term changes are happening as we grow old, and our organisms are actually losing the battle. So in my research, I mainly focus on protein oxidation, which happens due to the existence of free radicals. These free radicals, they can be both produced inside our cells due to metabolic activity of our cells, but they can also come from the outside of our organisms and cells from the environment. These free radicals can damage human cells. They can damage all biological molecules. However, proteins are the most vulnerable to protein oxidation, and proteins are also the most one of the most abundant molecules in our cells. So, why is protein oxidation important? One could say that protein oxidation that happens in living cells is just a side product, and there will be only very few molecules in the cell that will become modified, that will become damaged, and they have no importance for the overall survival of the organism. And yes, this is true. This is true in particular when we are young and our cells are able to renew. However, the proteins that become modified, they actually become irreversibly damaged and they lose their function. And by losing their function, they can contribute to pathology of different diseases. And one of the interesting issues that had been debated in the scientific field of redox biology is that it is not only the damage of the protein and loss of their function, but actually the biggest driver of pathologies and diseases are a gain of unwanted or unexpected function of these oxidized proteins. And here I list just a few of the pathologies that are related to protein oxidation. Some of them can be caused by chemical exposure, or one of those that is known to all of us is an exposure to sunlight, to UV light, that can cause both aging, skin aging, but it can also lead to cancer. We also have actually very often we also see protein oxidation and redox imbalance due to drug toxicity, and this can lead to liver or kidney damage. These are the external factors that can cause protein oxidation. We also have internal processes that involve generation of free radicals and protein oxidation. And these inflammation is one of those diseases with protein oxidation plays a really very, very important role in the pathology, and especially in a long-term inflammation processes that are involved in aging. So studying oxidized proteins is actually not very easy, and until recently we knew very, very little about what exactly happens with the protein and how it affects its structure and function. It is only the onset of really sensitive mass spectrometry and proteomics technologies that has allowed us to look in detail into what the free radicals are doing in the to the proteins and to their structure. And then from this, we can start analyzing what happens to the normal protein function and how it is affected and how it leads to pathologies and age-related diseases. So in my research, as Thorsten mentioned, I mainly use mass spectrometry and proteomics. And over the years, I have been developing several methods based on these technologies that allow us to study protein oxidation in detail. But all those fancy mass spectrometry methods, they wouldn't work if we didn't have proper models biological models for studying protein oxidation. And here I would like to say that studying protein oxidations is not easy, and also because it requires very sensitive and very reproducible model systems. Therefore, such studies are very difficult to perform in rodent models or directly from human tissue, because these biological systems are very, very complex, and it is very difficult to dissect the different interaction of the free radicals within these systems. So over the years, I have been using mainly models based on reconstructing extracellular matrix proteins, for example, and extracellular matrix environment, or I have used model of human skeletal muscle differentiation. I have recently also performed some studies using a 3D model of a human skin. However, as you would guess, since I am invited to this series of webinars, my favorite model for studying protein oxidation, especially in the context of drugs, chemicals, and xenobiotics mechanisms of function, is a three-dimensional model of human liver, which is based on human spheroids that are creating or that I create using cell vivo system. So over the years, we have analyzed the hepatocytes-based spheroids in different contexts, and also developed some methods that help us to understand what is happening in these spheroids. And this is what I would like to tell you about. And here in the next couple of slides, I will also tell you more details about a study that we have performed using these human or the hepatocytes-based spheroids to understand the toxicity and function of a drug called acetaminophen. But before I get to this, I just want to draw your attention to why I think, and in my research, spheroids have proven to be a very good model for understanding the redox imbalance in cells. So especially for drugs induced imbalance in the cells, we of course like to study these processes in hepatocytes, because this is where the first place where this redox imbalance happens. What is really challenging is that I am not so much interested in studying or defining the toxicity of drugs, rather interested in understanding the mechanisms of this toxicity of the drugs. And therefore, I prefer to work with therapeutic doses of drugs that are relevant to what is happening in our organism when we take a pill during our treatment. However, these therapeutic doses, they actually, of course, induce relatively small changes to our proteins and to our cells, because thanks to this, we can take the drugs and we survive the treatment. And therefore, it is quite technically challenging to detect these small changes and being able to analyze these small proteins. Oxidized proteins are also quite difficult to measure, not only because we have a low abundance of these proteins, but they also are quite reactive. So very often they form a lot of different products, and thus the signal that we would like to measure is diluted into many different forms. Therefore, we need a very sensitive system that is able to respond to the low or to the therapeutic doses of the drug, and also a system that is actually that allows us to control the environment in which the cells are in a very precise manner. So here, during my talk, you will actually see that I focus a lot on, or I put a lot of attention in my research with spheroids and 3D cell cultures into the control of the environment and reproducibility of the conditions that the cells are in. So let's get back to the story about the paracetamol or APAP, or we also call it acetaminophen. So I'm sure a lot of you know these names, and paracetamol or APAP is a very popular drug. It's an over-the-counter drug because it is considered very safe. And we use it quite often when we get headache, when we get cold, we have a pain in the throat, or maybe even we have a pain in our leg or back or other, even a tooth pain is, for tooth pain, the paracetamol or APAP is also prescribed. So this is a very, very popular drug, and also allowed for use in small children. And therefore, an overdose of this drug can actually happen quite easily. The overdose of paracetamol is usually accidental, but if it happens, it very often leads to liver failure, and is very difficult to reverse. The mechanisms of the acute toxicity of APAP are very well established, but actually very little is known, or much less is known, of what happens in the liver during a normal therapeutic treatment. And this is actually a very common problem, especially in elderly people that or people sick with other conditions that take paracetamol at the same time with other drugs. And also an interesting thing that maybe not a lot of people know is that paracetamol will also cause an increased liver, how to say, it will affect the liver metabolism also if we have, for example, been taking other drugs or maybe alcohol that are also in a way making our liver work harder. So it is important for us to understand what happens when we take a therapeutic dose of APAP and how our cells cope with this drug. So, as I said before, we already know quite a lot about APAP toxicity. And here is a scheme where I would like to take you through step by step, explaining what happens with APAP when we actually take the pill. So when we take the pill of APAP, it will, of course, dissolve in our blood, and it will end up very quickly in the liver. And in the liver, this chemical will be the majority of this chemical will be converted into a non-toxic products, which will be acetaminophen sulfate and glucuronide. This is a normal detoxification process that happens in the liver. However, a very small fraction of APAP is also metabolized by this special enzyme, P450E1, that can convert APAP to a very toxic metabolite and very reactive metabolite called NAPK. Now, because this NAPK is very toxic and very reactive, our cells immediately will gather defense mechanisms, mainly by producing reducing power that will remove the active metabolite. However, if we eat a lot of paracetamol, and if the overdose is, or the dose that we have taken is very high, our cells are not able to cope with the production of NAPK. They are not able to eliminate it, and then these NAPK will actively will react with other metabolites in our cells, very often cause protein adducts, and then will immediately lead to mitochondrial dysfunction and then apoptosis. So this will end up with our hepatocytes and our liver dying, and this is not very good for us. One of the mechanisms here, you can already see that these reducing agents that we have in the cells that are available for the cell to remove and to cope with the overdose or with the production of NAPK, these compounds will very quickly become depleted in the cell, and then this will lead to imbalance or redox imbalance in the cell. And this will immediately also lead to accumulation of other reactive and oxygen and nitrogen species in the cell, which are normally produced in the cell during a normal cell metabolism. This accumulation will lead to formation of different protein adducts, and this will lead to a damage of different cellular proteins. So this is what we were interested to look into. And our hypothesis in this study was that even therapeutic doses of paracetamol, APAP, can create a mild redox imbalance, so a mild oxidative environment in the cell, and this imbalance will trigger a cellular response that is both dependent on the creation or formation of the oxidized proteins in the cell, but it also will trigger a global cellular response where the cells actually want to cope and prevent the damage caused by the accumulation of reactive oxygen species. So we were lucky at that time to come across the prototype system for the clinostar and clinoreactors system, and we have started working with hepatocytes or hepatic cell lines-based spheroids. So the spheroids we use are based on are first created in microwells and pre-formed very tiny mini spheroids that consist of roughly 800 cells are there, then transferred into the rotating bioreactors, where they are actually allowed to grow and stay, so that they stabilize their metabolism and recover their functionality. So actually, from previous research and from the research of the Rogowska-Wrzesinska and Stephen Fay, we knew that this takes about 21 days. And so that the spheroids that we have been using for drug toxicity testing, they have been growing in and they have been maintained in the bioreactors for 21 days. And from 21 days, we have started the exposure to paracetamol. So one of the important things for us in these experiments was actually to find out the therapeutic dose of the paracetamol. And we have played with different concentrations that were relevant to therapeutic or similar to human therapeutic doses based on the cellular mass that we had in the bioreactor and compared to what happens in a human liver. So we have measured ATP production. So we have measured the cell fitness and happiness by looking at ATP levels in the cells. And we could see that at higher doses, when we treated the cells with higher doses, some of the very high doses caused cell death and loss of ATP already at a very, very early stage of the treatment. The 10 milligram dose was actually looked for a couple of days as if it didn't affect the cells, but then suddenly they also got dramatically affected and lost their ATP content. And then at the end, we found out that 2.5 milligram and 5 milligram, these were the doses where actually we could see that cells could be exposed to the 5 milligram dose every 48 hours. And even though we kept repeating this over several days, they were still able to maintain functionality and activity. So this was our therapeutic dose, and actually this dose also very well fits to the doses of APAP that are observed within the within this human liver when we take paracetamol tablet for headache. We were interested to look into protein oxidation, so we actually focused on two types of protein, or three types of protein oxidation. Two of them are cysteine oxidations. One is called cysteine S-nitrosylation, and the other one is called sulfenylation. I'm not going into details of the chemistry. What you need to remember is that these modifications are reversible. They cause temporary damage to the protein, but if there is enough reducing power in the cell, they can be reversed and they can be repaired. We also measured a carbonyl damage to proteins, which is a type of oxidation which actually cannot be reversed, or at least by now is considered as irreversible. And we also saw a slight increase in those this type of damage. However, the most significant increase was observed within the reversible cysteine oxidations. And of course, because mass spectrometry is my favorite tool to work with, we have applied some special methods, mass spectrometry-based methods that allowed us to quantify both the protein modifications, so the cysteine modifications, and also we were able to follow at the same time changes in protein expression. And we were actually very, very surprised to see that even though we saw virtual no differences in cell behavior and their ATP level, we could actually see that there was a lot of proteins that were affected in their abundance due to the paracetamol treatment. We have also found a large number of oxidized residues in the proteins that we have identified with the cysteine oxidations. And a lot of these changes, of course, they were supported by statistical analysis. So to cut the story short, we have mapped these, both the affected proteins, but also the affected oxidized proteins. We have mapped them into cellular networks, and we have put them on the landscape of cellular metabolism to understand actually what is happening in the cell. And here the scheme shows a schematic what happens inside the cell, and then the different colors indicate whether the proteins have been increased or decreased during the paracetamol treatment, and also whether they actually had modification on them. And we were very, very surprised to see that actually all or the majority of the proteins that we have identified to be modified, so oxidized, they were actually located to endoplasmic reticulum, and a lot of them were also associated with ribosomal proteins that are also located to endoplasmic reticulum. And this was very interesting, and it was a very unique found, because in most studies that are studying APAP toxicity at toxic acute doses, they find modifications and damage mainly to the mitochondrial proteins. However, it is obvious for us that after thinking and putting different results together, that the metabolism of NAPK will be happening at the endoplasmic reticulum. This is where all the P450 enzymes are located. And this is where the majority of the reactive oxygen species will be generated. And since these are short-lived species, they will also react with the proteins that are in a very close proximity. So this actually showed a very interesting result, that the initial damage or a redox imbalance during paracetamol treatment, it will actually happen in the endoplasmic reticulum and not in the mitochondria. Another interesting conclusion from our analysis was that these different changes to the proteins, they also affected the changes in cellular signaling. So what we hypothesize and is from our results is that these changes and these oxidized proteins, they trigger signaling cascades inside the cell. And we found that they are mainly these changes are triggering mainly WNT pathway and also NRF2 pathway. And these pathways are then activated to actually cope with the oxidative stress. So here I will just summarize, get back to my scheme with the hypothesis, where we discussed how APAP is metabolized into a dangerous NAPK metabolite, and that metabolite is actually removed by reduction And then we discussed that this reducing power in the cell is depleted and leads to the accumulation of reactive oxygen species and the formation of oxidized proteins. Now we can see with our results that these oxidized proteins, they actually trigger this signaling within the cell that both affects ubiquitin system in the cell and triggers a selective protein degradation. Most likely, we don't have any proof for that. That will be related to the removal of a damaged proteins that are completely damaged and cannot be repaired. We also see that this pathway will also affect the metabolism of the cell, and that will mainly focus on actually inducing the activity of cellular enzymes that can synthesize glutathione and increase the amount of a reducing power inside the cell, mainly via the pentose pathway, which of course can be used to cope with the NAPKI toxic NAPKI compound, but they also can cope and help to counteract the accumulation of reactive oxygen species. All right, so this is the end of the APAP story. And I hope you are as excited about this story as I am, because we actually, it took us a while to publish this study because it was very different from what normally is assumed that the APAP toxicity is doing inside the cell. But luckily, we have convinced the scientific community that looking at therapeutic doses of drugs is also very useful, and understanding the mechanisms of how the cells cope with the therapeutic doses is also very important. Because we know now that even it's very safe to take a pill of an APAP, we still will have some adverse effects on our cells, and our cells are challenged, and they have to actually do some extra work to cope with these byproducts. Okay, so I have only very few slides left, and I hope you will stay with me for that, because I would like to tell you also why I think that these HepG2C3A spheroids were actually the key success for our study. So we have decided to use this hepatocellular carcinoma cell line and not primary hepatocytes, because these cells are actually very, very stable. They can be used almost for an unlimited number of divisions. They have very stable genome. They are relatively cheap and easy to work with. And it has been shown by Rogowska-Wrzesinska and Stephen Fay, but also a lot of other researchers, that actually growing them in 3D cell cultures allows to recover these functions that are normally lost between the normal liver and 2D culture of the cells. What has proven to us also that was a key factor for success of our studies was keeping the system at a very high control. And that meant for us that we could obtain a very high reproducibility and very high sensitivity of our system. And one of the things you can do if you want to keep your system control, your spheroids, it is to monitor the growth pattern of the spheroids. You can find in many publications on how the spheroids will grow, but I recommend that you establish your own growth curve of your spheroids in your hands, and then follow and then monitor that growth curve in all your experiments. Why is it important? It is important because if you end up with a different, so indications of differences in the growth curve will indicate also that your environment in your spheroids has changed and it is not the same, and it can affect both the sensitivity and reproducibility of your system. What we also do in our lab, we also monitor what we call the Kleinerstadt biomass or population density. And what we mean by this, we basically count how many spheroids we have in the bioreactor at each stage. You can do it very easily by making photos of your bioreactors and by calculating the amount of spheroids and their protein mass. You can follow the biomass in your bioreactor. Again, this is very, very important because you will see deviations in the growth of your spheroids if you have different amount of spheroids in the bioreactor. Now, we have also looked at different ways of analyzing spheroids. We have performed cryosectioning and immunostaining so that you can look inside the spheroids. We have also developed methods for separating spheroids rim and core. And you can see, or you can read about these methods and see whether they are applicable for your research in the publications that we have published this year. We have also adapted a lot of different methods for use with spheroids. For example, the ATP assay, but also life and death staining, and we have also combined the spheroids or the use of spheroids with a lot of different downstream methods. All that you can see is these publications. If you are more interested how to use these methods, or of course you can also write to me at any time. So before I end, I would like to say that for us, in our hands, the HepG2C3A spheroids are a very accurate model for human toxicity or for studying the mechanisms when we apply a near therapeutic doses of drugs. Combined with proteomics, in my lab, it proved as a very, very sensitive a very sensitive tool, allowing us to dig into very tiny mechanistic aspects of drugs toxicity. And then, of course, what I already said before is, in my experience, controlling the cell growth environment is the key for obtaining reproducible and sensitive results. Okay, with that, I would like to thanks for your attention, and then I'm ready to take any questions.
Good. Thank you very much, Adelina, for a very nice talk again. It's always a pleasure. I have a few questions. First question is, how have the spheroids been treated with APAP?
We dose the spheroids with every 24 hours, every 48 hours during the media change. And then, of course, we calculate the amount of the drug that is provided to the bioreactor based on the bioreactor biomass. In all our experiments, before we start the treatment of bioreactors. So we make sure that the bioreactors actually contain the same amount of spheroids. And we do that already from the day 7, where we monitor the population or the number of spheroids in the bioreactor. So we make sure that in each bioreactor we have the same amount of cells or proteins and spheroids, and then the dose of the drug is calculated from that.
Okay, that makes quite good sense. Have you measured the NAPQI levels in the cells?
Yeah, that's a very good question. No, we didn't measure that.
Okay. Can you measure the ATP levels in the bioreactors?
No, so we measure the ATP levels in the cells or in the spheroids that we take out from the bioreactor. So we lyse the cells and perform ATP assay outside the bioreactor. So that requires, of course, that we remove some spheroids from the vessel.
Okay. So when you do the spheroid sectioning, are then they paraffin embedded or?
So in our hands, the best option is to put the spheroids into OCT. So like we use tissue tech and not the paraffin. We also perform mainly cryosectioning of the spheroids and immunostaining. So this is why that's the best method for us.
Okay, thank you. How is the flow cytometry performed on the spheroids?
So, as I said very quickly, we have developed a method to disassemble spheroids by very gentle trypsinization and mechanical disintegration of the cells or of the spheroids. So you can, by performing very gentle disintegration, you can obtain a single cell suspension from every spheroid, and then you can perform more or less any type of flow cytometry, including flow cytometry where you use antibody staining for analyzing specific markers in the cells.
Okay, thank you. Then I have one more. Do you know how stable the APAP is in your media?
Yes, this is a very challenging problem. So of course we haven't measured the APAP stability, and it is known that it takes about 18 to 12 hours for the APAP to become to be destroyed in the cell culture media. However, in these experiments, the dose was very, very low, and we simply assumed that whatever had been taken up by the cells was enough to affect their metabolism and affect the protein oxidation. And because we wanted to see the repeated dosing over a prolonged period of time, we have assumed that the next dose, a fresh dose after 48 hours, will provide a new molecules of the drug. But we haven't monitored its stability.
When you do this repeated dose, do you then see an accumulation of APAP or its metabolites within the spheroids?
So we only see the accumulated effect on cells activity. So for example, with the 10 milligram dose, we could see that the cells didn't die during the first 2 days, but after the third dose, they became affected and could not cope with the drug anymore. Therefore, we assume that this is a sign of an accumulated effect of the drug.
Okay, makes sense. Then I have one question. It might be a bit difficult to answer. So it is, what is the function of the bioreactor and how to monitor the inside concentrate of cell factors in real time?
Well, this is a very interesting question, and I guess it could also be addressed to cell vivo developers. One of the ways that you can use to monitor what is inside or what is secreted by the cells is, of course, to remove media from the bioreactors during the incubation of the spheroids in there. And depending on how much material you or how much media you need, it is possible to do that also between actually the actual media change of the bioreactors. So, for example, in this way, you can monitor the level of glucose and the glucose consumption, because the glucose test is very sensitive, and you need only 100 microliters of the medium. So what we do, we will take only 100 microliters of the media from the bioreactor, and then, of course, replace the missing volume with a fresh medium. And we allow ourselves to assume that this 100 microliters in a volume of 10 milliliter does not affect significantly the cell environment and cell behavior.
Well, I think it's less than 1%, right? So
yeah, well, yes, I hope that that answers the question, but otherwise I don't know of a way where you could monitor this different secreted compounds by not removing the media. Perhaps some specific markers could be added, but for now I don't know of any way other than removing a tiny little bit of media and analyzing it outside the bioreactor.
I have another question here. So it says how to decide the size of spheroids for experiments.
Mm-hmm. Thank you so much for this question. I think it's a lot of scientists struggle with that question, and one could say this is, of course, cell type dependent, and it also very much depends on what you would like to study. In our hands, as you saw from the growth curve, in our hands, the spheroids grow very rapidly, up to 14, 16 days. And after that, they kind of stabilize the growth. They continue to grow, but the growth is very, very slow. And this has been studied by others extensively, and this is attributed to the slower growth rate of the cells that don't that when not trypsinated, they will not divide very fast. And in our hands, this is the best time to actually start some exposure treatment experiments or analysis. So when the growth of the spheroids stabilizes. Now the size of the spheroids will very much depend on what we call a population density. So the more spheroids you have in your bioreactor, the smaller they will be, because they are limited by the amount of food we give them. The cells that we use, they grow in a low glucose medium. So that means that around after 8 in our hands with 150 spheroids per bioreactor, around after 8 to 10 hours, all the glucose is depleted. And then for the remaining time until the next media change, which is performed every 48 hours, they have to use what they have accumulated in form of the glycogen. So if you have less spheroids in your bioreactor, they will have more food to eat. There will be less kids to share the food on the table, and then they will grow faster. And then it's a matter of what works for you. For us, around the size of the spheroids, around 18 to 21 days. This is approximately 1 or 1.2 millimeter spheroids.
Good. Can you actually measure the glycogen level in your cultures?
Yes, yes. Yes, we can measure the glycogen in the cultures, and also the glucose in the media. So it is we can see that the glucose that is taken up by the cells, it is then accumulated in form of glycogen that is then gradually used by the cells until the end, or until they get new food. And if you start working with a new cell line, it is I would always recommend that you monitor this glucose uptake, glycogen production, if this is of course relevant, because that will also allow you to understand the metabolic needs of your clinoreactor cultures, and how many spheroids you should actually keep in the culture. Because if the cells deplete glucose too fast, and then they are not able to store enough glycogen that lasts until you feed them again, the cells will starve and they will start to die. And once the cells start to die in spheroids, this process happens very, very rapidly, and is impossible to stop.
Thank you very much. It's a very good comment there, that you need to monitor if your kids are starving to death,
Yeah.
or,
Yes.
or not.
Yeah.
So
Sure.
I think unless I have any other questions, and I don't see I have that, then I think I will conclude the talk for today.
Yep.
And I would like to thank you again. I have someone saying that there should be a question from the panel, but I can't see that. So I will thank you once again, Adelina. And if anyone has any questions, please feel free to contact either Adelina or us at Soluble, and we will be happy to forward them.
Yes. Thank you very much.
Thank you.